Welcome to another episode. Before we begin, I'd love to know where you're listening from and what time it is for you right now. Drop a comment and let me know. It's always fascinating to see how this journey connects people across the world. And if you enjoy these explorations, don't forget to subscribe so you can join in whenever we set off on another voyage through knowledge. Tonight, we're going to drift into the Milky Way. Not the bright sweep of stars we all know, but the dark lanes that cut through it. At first glance, they look like gaps, like pieces missing from the galaxy. But in reality, they are not emptiness at all. They are filled with something ancient, delicate, and mysterious: cosmic dust. These dust lanes stretch across thousands of light years, vast rivers of shadow winding through the heart of our galaxy. To the naked eye, they look like darkness, but behind that darkness lies the very material from which stars and planets are born. Without these lanes of dust, there would be no Earth, no sun, no us. Astronomers once thought these were voids in the heavens, patches where stars simply didn't exist. Over centuries, through myths, telescopes, and patient measurements, they discovered a truth stranger than the legends. That darkness in the sky is not absence, but presence. A veil of microscopic grains, so small you could line thousands of them across the width of a human hair, yet so abundant they can blot out the light of entire constellations. In this episode, we're going to follow the dust. From ancient myths of the Milky Way, to Galileo's first glimpse of its crowded stars, to the 20th century astronomers who realized why parts of it looked dim and red. We'll explore how modern observatories, from radio dishes to space telescopes, peel back that veil, revealing hidden star nurseries and the deep structure of our galaxy. And we'll ask what it means, on a poetic level, that the same dust which hides the stars also creates them, that we are quite literally born from the darkness between the lights. So settle in, get comfortable, and let's step into the shadows of the Milky Way. When you look up at the night sky on a dark, moonless evening, far away from the glow of cities, there's one sight that has captivated humanity since the beginning of history: the Milky Way. It stretches across the heavens like a pale, misty river, a band of light so wide and diffuse that it doesn't look like individual stars, but rather like a soft glow painted onto the dome of the sky. To the naked eye, the Milky Way seems almost like a road or a pathway, something grand and purposeful. And for most of human history, people believed that it was exactly that. The earliest humans saw the Milky Way long before they had any idea of what stars even were. To them, it was a mystery that demanded an explanation. And explanations came in the form of stories, mythologies that tried to account for why a glowing band divided the sky. These myths are windows into the way ancient civilizations understood the universe, long before telescopes or astrophysics. In ancient Greece, the Milky Way was tied to the gods. The name itself, Galaxias Kyklos, means milky circle in Greek. One of the most enduring myths says that it was created from the milk of Hera, queen of the gods. The story goes that when Heracles, the infant who would later become the hero Hercules, was brought to nurse at Hera's breast, the goddess pulled away in anger. Her milk sprayed across the sky, forming the glowing river of stars we now call the Milky Way. The imagery was vivid enough that the name stuck, carried into Latin as Via Lactea, the Milky Road. From there, the name passed into European languages, eventually becoming simply the Milky Way. The Greeks weren't alone in weaving stories about this luminous band. The Romans saw it too as a divine road across the heavens. Meanwhile, in northern Europe, the Vikings and other Norse peoples saw the Milky Way as the path of the dead, guiding fallen warriors to the halls of Valhalla. In Finland, it was called the Pathway of Birds, as migratory birds seemed to follow it across the night sky. Farther east, in China, the Milky Way was known as the Silver River. One of the most famous legends tied to it is the story of the Weaver Girl and the Cowherd, two lovers separated by the River of Stars. According to the myth, they are allowed to meet only once a year, when a bridge of magpies forms across the Milky Way. This story is still celebrated in China during the Qixi festival, sometimes called the Chinese Valentine's Day. It shows how a celestial feature became part of cultural rituals that survive into the modern world. The Inca civilization in South America had a very different interpretation. For them, the Milky Way was not just a bright river, it was literally a river, the celestial counterpart of the Vilcanota River, which flows through the Sacred Valley in Peru. They called the Milky Way Mayu, and within its dark patches they saw shapes of animals, a llama, a fox, a serpent. Unlike Western traditions, which focused on the bright parts of the Milky Way, the Inca built constellations from the dark regions, the very dust lanes that puzzled European astronomers centuries later. These dark constellations were believed to influence agriculture and life on Earth, a striking reminder of how different cultures interpret the same sky in unique ways. The Aboriginal peoples of Australia also had stories tied to the dark bands in the Milky Way. To some groups, the central bulge and its surrounding dust lanes represented an emu stretched across the sky. The emu in the sky is still visible in the southern hemisphere. Its head lies in the dark Coalsack Nebula near the Southern Cross, and its body runs along the dust lanes of the galaxy. For Aboriginal cultures, this figure guided seasonal activities such as hunting and gathering. Once again, it was the darkness within the Milky Way, rather than its brightness, that held meaning. Across Africa, Asia, the Americas, and Europe, countless myths used the Milky Way as a backdrop for human imagination. Whether as spilled milk, a silver river, or a road to the afterlife, the galaxy was seen as a bridge between the human world and something greater. And in almost every case, these interpretations were poetic, rooted in story rather than science. But they set the stage for a long human fascination with the ribbon of light above. The turning point came with the invention of the telescope in the early 17th century. In 1609, Galileo Galilei pointed a crude telescope at the heavens. What he saw changed our understanding forever. In 1610, he published his findings in a small book called Sidereus Nuncius, the Starry Messenger. Inside, he described the wonders he had seen, the craters of the moons of Jupiter, and the astonishing revelation that the Milky Way was not a glowing mist, but a dense multitude of individual stars. Galileo wrote that the Milky Way is nothing else but a mass of innumerable stars planted together in clusters. For the first time, humanity understood that the band across the sky was not a mystical fog, but the collective light of billions of suns. Yet Galileo also noticed something puzzling. The Milky Way was not uniformly bright. In places, there were dark patches, gaps where no stars seemed to shine. These features stood out, particularly in the regions near the constellations Cygnus and Sagittarius. To Galileo, it seemed as if the stars simply weren't there, as though the heavens had holes cut into them. The concept of interstellar dust did not yet exist. No one imagined that particles smaller than a grain of sand could obscure the light of distant suns. To early telescopic observers, these were just cosmic voids. Over the following centuries, astronomers mapped the Milky Way more carefully. They drew detailed star charts, noting where the galaxy seemed rich with light and where it seemed oddly depleted. In 1755, the German philosopher Immanuel Kant proposed that the Milky Way was a flattened disk of stars, which explained why it appeared as a band in the sky. William Herschel, in the late 18th century, counted thousands of stars in different directions and confirmed that the Milky Way was disc-shaped. But even Herschel, with his massive telescopes, still thought the dark patches were regions without stars, simply empty space. This idea persisted well into the 19th century. The Great Rift, the striking dark lane that splits the summer Milky Way from Cygnus down through Aquila and into Sagittarius, was often drawn in atlases as if it were a literal hole in the stellar distribution. The Coalsack Nebula in the southern hemisphere was labeled as a void, a place devoid of stars. Astronomers puzzled over these features, but they had no framework to understand them. It seemed absurd to imagine that space was filled with dust thick enough to blot out starlight, yet somehow invisible to the naked eye. In a sense, this misunderstanding was natural. Human experience with dust is earthly. It collects on shelves, floats in a sunbeam, or clouds the air in a desert storm. The idea that the vast gulfs between stars could be filled with tiny grains of carbon, silicates, and ice was so far removed from daily life that it hardly seemed plausible. For generations, the Milky Way's dark lanes were thought of as absences, gaps in the great celestial tapestry. And yet, the myths of cultures like the Inca and the Aboriginal Australians, who looked at the dark shapes and saw animals and rivers, had grasped something closer to the truth. They recognized that the darkness was not emptiness, but presence, something real that shaped the night sky. It would take the careful work of 20th century astronomy to prove them right, to show that the shadows in the Milky Way were made not of nothing, but of something profoundly important: interstellar dust. This shift, from myth to telescope, from the poetry of spilled milk to the physics of starlight blocked by microscopic grains, marks one of the great journeys in human understanding. The Milky Way went from being a symbol to a structure, from a story told around the fire to a subject of precise measurement. And in those dark patches, once dismissed as gaps, lay the key to understanding how galaxies evolve, how stars are born, and ultimately how we came to exist. When you gaze at the Milky Way on a clear summer night, you notice that the great river of stars is not uniform. It looks mottled, streaked with dark patches and jagged bands that carve through its brilliance. To the naked eye, they seem like tears in the fabric of the galaxy, empty spaces where starlight simply stops. But these are not voids at all. They are what astronomers call dust lanes, colossal structures of interstellar matter that weave across the galaxy like shadows drawn against the stars. So what exactly are they? A dust lane is a region of space filled with interstellar dust, tiny solid particles made of elements like carbon, silicon, oxygen, and iron, often coated with frozen molecules such as water or ammonia. These grains are unimaginably small, typically only a fraction of a micron across. To put that in perspective, a single grain of dust in space is smaller than a particle of cigarette smoke, smaller than the wavelength of visible light. If you lined up thousands of them, they would barely stretch across the width of a human hair. And yet, despite their minuscule size, they are present in such staggering numbers, spread across such enormous expanses, that together they can block the light of entire star fields. Imagine holding a fine mist of smoke in front of a lamp. Each particle is nearly invisible on its own, but in vast quantity, the smoke dims the light. That is what interstellar dust does on a galactic scale. When light from distant stars tries to pass through a dust lane, it is scattered and absorbed. Shorter wavelengths, like blue and violet light, are scattered more strongly than longer wavelengths, so the starlight that does manage to slip through often looks redder. Astronomers call this process interstellar extinction and reddening. To our eyes, the dust lanes simply appear black, as if someone has erased part of the sky with a charcoal brush. But here's the fascinating part. The dust isn't actually dark. In reality, it glows faintly in infrared and sub-millimeter wavelengths. The grains absorb energy from starlight, warm up to just a few tens of degrees above absolute zero, and then re-radiate that energy as long wavelength light. To a telescope sensitive to infrared, a dust lane lights up like a glowing river of heat, bright and structured. The darkness is an illusion of our human eyes, which are tuned only to the narrow band of visible light. Where we see absence, an infrared detector sees abundance. This dual nature, dark to us, luminous to machines, has profound implications. It means that for centuries, humans thought dust lanes were empty space until technology gave us eyes that could see in other colors. With the advent of infrared astronomy in the mid-20th century, satellites like IRAS in 1983 and Spitzer in 2003 revealed the Milky Way's dust in breathtaking detail. Suddenly, the gaps in the galaxy weren't voids, but rivers of glowing matter, sculpted into filaments, tendrils, and billowing clouds. But what is the true scale of these structures? That's where the story turns astonishing. Dust lanes are not local phenomena. They are galactic architecture. Many stretch across thousands of light years. For example, the Great Rift, the vast dark lane that cuts through the summer Milky Way, is about 800 light-years away and extends for thousands of light-years along the galactic plane. Within it lie massive molecular clouds, some hundreds of light-years wide, containing enough raw material to form millions of new stars. Closer to the galactic center, dust lanes are even more prominent. The Milky Way is a barred spiral galaxy, and along the bar structure at its core, two immense dust lanes funnel gas inward. Each one is thousands of light-years long and tens of light-years thick. These are not wisps or threads. They are titanic rivers of dust and gas, dwarfing anything we can comprehend on human scales. To cross one in a spacecraft traveling at the speed of light would take longer than all of recorded human history. Astronomers have measured that roughly 1% of the Milky Way's interstellar medium by mass is dust. That might not sound like much, but consider the total. The Milky Way contains around 100 billion solar masses of gas and dust. That means there are over 1 billion solar masses worth of dust grains drifting through space, more than enough material to build countless Earths, Jupiters, and stars. These dust grains are the seeds of future worlds, scattered in bands that cut through our galaxy like scars. One might ask, if dust lanes are so massive, why don't we see them stretching across the entire sky? The answer is geometry. The Milky Way is a flat, rotating disk about 100,000 light-years in diameter and roughly 1,000 light-years thick. From our position inside the disk, about 2/3 of the way out, we're looking edge-on into the galactic plane. That's why the Milky Way appears as a narrow band instead of a full circle. Dust lanes are concentrated along this plane, where stars are most densely packed and where gas and dust settle like sediment in a river. From Earth, these lanes trace the structure of the galaxy's spiral arms. They align with the places where new stars are forming, where gas is compressed and cooled. In fact, astronomers often use the location of dust lanes to identify spiral arms in distant galaxies. Look at photographs of the Andromeda Galaxy or the Sombrero Galaxy, and you'll see the same patterns, bright swirls of starlight cut through by dark streaks of dust. Our Milky Way is no different, except we're inside it, looking out. There's also a curious psychological aspect to them. To our eyes, dust lanes can seem unsettling, even ominous. The night sky is supposed to be a canvas of stars, and when a thick black band cuts through it, it feels wrong, like something has been erased. It's easy to see why early astronomers thought these were voids. But once you know the truth, that these shadows are not emptiness but matter, the perspective changes. The darkness becomes alive, not a hole in the sky, but a womb for stars. Some of the most famous dark nebulae, such as the Horsehead Nebula in Orion or the Pipe Nebula in Ophiuchus, are parts of these dust lanes. To the naked eye, they're black shapes. In astrophotography, they're haunting silhouettes against glowing backgrounds. And within them, invisible to us, countless protostars are forming, each one wrapped in cocoons of dust. So when we ask, what are dust lanes? The answer is not just bands of dust that block light. They are the skeleton of the galaxy, marking where stars are born, where spiral arms take shape, and where cosmic recycling happens. They are the archives of stellar death, ashes of old suns scattered into space, and the cradles of stellar birth. They are both obstacle and opportunity, hiding light yet creating life. It's almost poetic that something so small, a dust grain smaller than a speck of smoke, can shape the structure of galaxies. Multiplied by untold trillions, these grains become curtains drawn across starlight, visible from thousands of light years away. They remind us that in the universe, scale is everything. What seems insignificant on the level of atoms can, on the scale of galaxies, reshape the cosmos. And yet, for all their grandeur, dust lanes were misunderstood for centuries. To early observers, they were merely holes. To modern infrared eyes, they are radiant rivers of matter. The truth, as always in science, is stranger and richer than first impressions. When we speak of the vast dark lanes that stretch across our galaxy, it's easy to imagine them as clouds in the ordinary sense, like the billowing shapes we see on Earth, made of water droplets and vapor. But the truth is far stranger and far more delicate. Interstellar dust is not like the dust you find on a bookshelf, nor like the soot from a fire, though in some ways it resembles both. It is a substance at once humble and profound, the fine debris of stars scattered into the void, drifting across light years. At the most basic level, interstellar dust grains are tiny solid particles. Their sizes are almost impossible to picture. The typical grain measures about 0.1 microns in diameter. That's a tenth of a micrometer, or 1/10,000th of a millimeter. If you plucked a single hair from your head and laid dust grains along its width, you could line up thousands across it. Compared to familiar things, they are much smaller than pollen grains, smaller than bacteria, and closer in size to the particles of smoke you see curling upward from a candle flame. And yet, despite their invisibility to the naked eye, these grains matter. Collectively, they shape the appearance of galaxies, blotting out starlight and reddening the glow of distant suns. Their composition, forged in the hearts of ancient stars, determines not only how they scatter light, but how they seed the formation of new worlds. So what are these grains made of? Most are composed of silicates and carbon-based materials. Silicates are minerals rich in silicon and oxygen, the same basic stuff that makes up much of Earth's crust. In space, they often exist as tiny crystals, olivine and pyroxene, familiar to geologists as the greenish minerals you might find in volcanic rocks. These silicate grains are often coated with mantles of ices, frozen water, methane, ammonia, carbon dioxide. The conditions of interstellar space are cold, just a few tens of degrees above absolute zero. So atoms and molecules that would normally float as gas can freeze onto the surfaces of dust grains like frost, forming on a window in winter. Then there are the carbonaceous grains, particles made of graphite-like carbon, amorphous soot, and complex organic molecules. Some of these are polycyclic aromatic hydrocarbons, or PAHs, flat, ring-shaped molecules of carbon and hydrogen that resemble the structure of coal or tar. PAHs are remarkable because they may have played a role in the chemistry of life on Earth. These molecules can absorb ultraviolet light and re-emit it in the infrared, giving interstellar clouds a faint glow detectable by space telescopes. In addition to silicates and carbon, dust grains can also contain iron, nickel, and other heavy elements, relics of supernovae, where the periodic table itself was forged. Many grains are thought to begin as tiny cores of refractory minerals, hardy compounds like corundum or spinel, formed in the cooling atmospheres of old stars. Around these cores, layers of carbon or silicates condense, building grains that are tough enough to survive the harsh radiation of space for millions of years. Where does this dust come from? The answer is written in the life cycles of stars. When a star like our Sun nears the end of its life, it swells into a red giant. In its outer layers, heavier elements, carbon, oxygen, silicon, are formed through nuclear fusion. The star begins to shed its outer material into space, creating a planetary nebula, a glowing shell of gas and dust that expands outward over tens of thousands of years. Within that outflow, dust condenses, grain by grain, like tiny crystals forming in cooling vapor. These grains are then cast adrift into the interstellar medium, where they will travel for millions of years, colliding, clumping, and sometimes being destroyed by radiation. In even more dramatic fashion, supernovae create dust in colossal quantities. When a massive star reaches the end of its life, its core collapses and its outer layers explode outward with tremendous force. In that explosion, temperatures and pressures rise to such extremes that heavy elements are forged, iron, nickel, and beyond. As the debris expands and cools, dust grains condense out of the superheated gas. A single supernova can create up to a solar mass of dust, enough material to build hundreds of thousands of Earths. Observations of supernova remnants, like the famous Crab Nebula or Cassiopeia A, reveal thick clouds of dust glowing in the infrared, fresh material injected into the galaxy's bloodstream. But dust is fragile. Supernova shockwaves and high-energy radiation can destroy grains as easily as they create them. This means the dust content of the galaxy is a balance between creation and destruction. Some grains are shattered, others eroded, but enough survive to accumulate across billions of years. It is a cycle, one of cosmic recycling on the grandest scale. This recycling is essential to galactic evolution. Every generation of stars enriches the interstellar medium with heavier elements and dust. That dust, in turn, helps form the molecular clouds that collapse into the next generation of stars. Without dust, gas would have a harder time cooling and fragmenting into dense clumps. Without dust, planets might never coalesce from disks around young stars. Without dust, organic molecules might not form as easily on the surfaces of grains, where they can combine into ever more complex chemistry. In this sense, the dust lanes we see in the Milky Way are not just obstacles to light. They are the breeding grounds of creation. They represent the ongoing cycle of matter in the universe. Stars are born, live, and die, and their ashes seed the birth of new stars. From those new stars emerge planets, and on some of those planets, life. The atoms in our bodies, carbon in our cells, iron in our blood, silicon in our bones, were once dust grains drifting through interstellar space. Carl Sagan's famous phrase, "We are star stuff," is literally true. And much of that star stuff spent millions of years as interstellar dust before being incorporated into the Earth. The cosmic recycling of matter is one of the most humbling ideas in modern science. Think of it this way: the oxygen you breathe was once forged in the core of a star. The calcium in your teeth may have traveled the galaxy as part of a dust grain before settling on Earth. When you look up at the dust lanes of the Milky Way, you are not just seeing shadows in the sky. You are looking at the very material that built you. Astronomers study this composition through many clever techniques. Spectroscopy allows them to see which wavelengths of light are absorbed by dust. Silicates, for instance, have a characteristic absorption feature at about 10 microns in the infrared, a fingerprint of their molecular bonds. Carbon-rich grains have their own distinct signatures. By comparing the spectra of starlight that passes through dust clouds with laboratory measurements of minerals on Earth, scientists can reconstruct the composition of grains light years away. In recent years, missions like the Spitzer Space Telescope and the James Webb Space Telescope have pushed this research to astonishing detail. Webb, for instance, has detected ice mantles on dust grains in molecular clouds, revealing water, ammonia, and even complex carbon molecules frozen in place. These ices act as chemistry labs in space, enabling reactions that would not otherwise occur in the thin gas of the interstellar medium. Some scientists even speculate that the building blocks of life, amino acids, sugars, may form on dust grains and later be delivered to young planets. So, interstellar dust is not just passive dirt. It is an active participant in cosmic evolution. It hides light, but it also makes light possible by enabling stars to form. It seems fragile, but in aggregate it sculpts galaxies. It is, in every sense, the connective tissue of the cosmos, linking death to birth, past to future, stars to life. And when you step back and think about the dust lanes of the Milky Way, it becomes clear they are not just dark bands blocking the stars. They are the living memory of the galaxy, a record of all the stars that came before, a promise of those yet to come. For centuries, astronomers thought of the Milky Way's dark lanes as voids. Even as telescopes revealed more and more stars within its misty band, the shadows cutting across it were still interpreted as cosmic absences, places where stars simply didn't exist. It took until the 20th century for the true explanation to emerge, that space between the stars was not empty at all, but filled with a thin haze of dust capable of dimming and reddening the light of distant suns. The turning point came in the 1930s, when a Swiss-American astronomer named Robert Julius Trumpler solved a long-standing puzzle. His discovery would not only reveal the true nature of interstellar dust, but also reshape humanity's picture of the galaxy itself. Trumpler was studying open clusters, groups of stars loosely bound together by gravity. Unlike globular clusters, which are dense and spherical, open clusters are irregular gatherings of a few dozen to a few thousand stars, often relatively young. They're scattered throughout the plane of the Milky Way and serve as excellent laboratories for understanding stellar properties. At the time, astronomers believed they could estimate the distances to these clusters by comparing two methods: the apparent brightness of their stars and the angular size of the cluster in the sky. A nearby cluster would look both bright and large, while a distant one would look faint and small. The two measures should scale consistently. But Trumpler noticed something odd. When he compared the apparent sizes and brightnesses of dozens of open clusters, the numbers didn't agree. Distant clusters weren't just fainter because they were farther away. They were much fainter than expected. At the same time, their apparent sizes suggested distances that didn't match their brightnesses. Something invisible was interfering with the light. In 1930, Trumpler published his landmark paper. He concluded that starlight was being absorbed and scattered by material in space. The farther away a cluster was, the more of this material its light had to pass through, making it look dimmer than distance alone could explain. He estimated that the effect amounted to about 1 magnitude of dimming per kiloparsec, a kiloparsec being about 3,260 light-years. Every time light traveled that distance through the galactic plane, it became roughly 2.5 times fainter. This was the first quantitative proof that interstellar extinction exists. The idea was revolutionary. Astronomers had long assumed that space between the stars was essentially transparent. After all, when you look at the night sky, starlight reaches us from hundreds of light-years away. But Trumpler showed that the universe is not perfectly clear. It has a kind of cosmic fog, thin enough to see through on small scales, but thick enough to distort our view of the galaxy when stretched across thousands of light-years. His discovery also explained another long-standing mystery: why some distant stars appeared unusually red. As light passes through dust, shorter wavelengths, blues and violets, are scattered more effectively than longer wavelengths like red and orange. This is the same principle that makes Earth's sky blue during the day and red at sunset. In interstellar space, the result is that starlight becomes both dimmer and redder the farther it travels. Before Trumpler, this reddening had been noticed but not understood. After his work, it became clear. The redness of distant stars was not intrinsic to them, but a side effect of dust. This realization changed everything about how astronomers mapped the Milky Way. Before Trumpler, attempts to measure the galaxy's size and structure relied heavily on counting stars. William Herschel, in the 18th century, had tried to map the Milky Way by counting how many stars he saw in different directions. He assumed that more stars meant looking deeper into the galactic disk, while fewer stars meant reaching its edge. By this method, he concluded that the Sun lay near the center of a relatively small, irregularly shaped galaxy. But Herschel didn't account for extinction. Dust lanes had fooled him. They made distant regions appear empty of stars, tricking him into thinking the galaxy was smaller and more uneven than it really was. Even in the early 20th century, astronomers underestimated the size of the Milky Way because they didn't realize how much light was being blocked. Trumpler's work forced a recalibration. Once extinction was included, the galaxy's true scale came into view. About 100,000 light-years across, far larger than earlier estimates. The Sun was not at the center, but out in one of the spiral arms, 2/3 of the way from the core. At first, the idea of widespread interstellar dust met with skepticism. The notion that empty space was filled with enough matter to dim starlight seemed implausible. After all, dust was supposed to settle on bookshelves, not drift across cosmic distances. But evidence piled up quickly. In the 1930s and 40s, astronomers like Bengt Strömgren and Bart Bok studied the distribution of dark nebulae and found that extinction correlated with visible dark clouds. By the 1950s, radio astronomy provided further support. Observations of the 21-centimeter line of neutral hydrogen revealed dense regions of gas coinciding with dust. The once controversial idea became standard science. Trumpler's discovery did more than correct maps of the Milky Way. It opened an entirely new field, the study of the interstellar medium. Suddenly, astronomers realized that the space between stars was not empty at all, but filled with a complex mix of gas, dust, and magnetic fields. This medium was not just a nuisance dimming starlight, but the raw material for new generations of stars and planets. By recognizing extinction, astronomers could also correct for it. Measuring how much a star's light was reddened and dimmed provided a way to estimate how much dust lay between us and the star. This became a tool not just for mapping dust lanes, but for probing the structure of the galaxy itself, and the implications reached farther still. Extinction affects our view of other galaxies too. When we look outward, the dust in our own galaxy veils our perspective. Correcting for it is essential for everything from measuring cosmic distances to understanding the expansion of the universe. There is something poetic about Trumpler's discovery. For millennia, humans told stories about the Milky Way's dark patches, llamas, emus, spilled milk, not knowing what they were. Early astronomers mapped them as voids. And then a quiet puzzle about open clusters revealed that these shadows were not empty, but full. The cosmos was not transparent, but layered with veils, woven from the ashes of ancient stars. The discovery of interstellar extinction reminds us of how much our senses can deceive us. Darkness can mean light hidden, not light absent. What looks like emptiness can be fullness in disguise. And sometimes the most profound truths in science begin not with a spectacular revelation, but with a discrepancy in data, patiently followed to its conclusion. Robert Trumpler's 1930 paper might not have had the dramatic flair of Galileo's Starry Messenger or Edwin Hubble's proof of galaxies beyond the Milky Way. But in its quiet way, it reshaped our cosmic map. It revealed that the Milky Way's dust lanes are not just tricks of the eye, but fundamental features of galactic structure. It showed that the shadows in the sky are not voids, but archives of stellar history, containers of the future. Today, every astronomical measurement that deals with distance, brightness, or color accounts for extinction. Every time we look at a star through the telescope, we're aware that some of its light has been dimmed and reddened by dust. And every time we look at the Milky Way, we know that its shadows are not absences, but presences, dust lanes that mark where matter lingers between stars, shaping the galaxy's evolution. When most people imagine the Milky Way, they picture a broad sweep of light arcing across a summer sky, dense with stars. But what's equally striking, if you watch closely, are the dark patterns carved through that river of brightness. They are not random. Dust, subtle and invisible in small amounts, sculpts the appearance of our galaxy on the grandest scale. Without it, the Milky Way would look altogether different. From Earth, we see the Milky Way edge on. Our solar system sits about 2/3 of the way out from the center, embedded in the galactic disk, so when we look into the plane of the galaxy, we peer through a long, crowded corridor filled with stars, gas, and dust. This perspective is why the Milky Way looks like a band rather than a sphere. But that band is not uniformly bright. Dust, concentrated along the same galactic plane as the stars, carves away at the light, giving the Milky Way its mottled, broken appearance. Near the center of the galaxy lies a great bulge of stars. If space were perfectly transparent, the bulge would dominate our night sky, a glowing golden swell of light in the direction of Sagittarius, brighter than any other feature. But we never see it that way. Between us and the galactic center lies a thick concentration of interstellar dust that obscures most of the bulge from visible light. In fact, entire regions of the inner galaxy are hidden, invisible to the human eye or even optical telescopes. This was one of the great frustrations of 19th century astronomy. Everyone knew that the center of the Milky Way must lie somewhere in Sagittarius, but the dust was so pervasive that the structure behind it could not be mapped. It was only with radio and infrared astronomy in the 20th century that the true extent of the galactic bulge came into view. Closer to home, dust lanes have a more direct impact on what stargazers see. The most obvious example is the Great Rift, a dramatic series of dark bands that split the Milky Way lengthwise from the constellation Cygnus in the north, down through Aquila and into Sagittarius. On a clear night, especially in July or August, the Great Rift is unmissable, a wide, dark gash running through the brightest part of the Milky Way. It looks almost as though a hand has torn the galaxy apart, separating it into two glowing streams. The Great Rift is caused by enormous molecular clouds lying only a few hundred light-years from Earth. These clouds, stretching across thousands of light-years, are dense with dust and gas. They blot out the light of more distant stars, creating the illusion of emptiness. But in reality, behind the rift lies the full density of the galactic disk. We simply can't see it in visible light. For observers with binoculars or a small telescope, the Great Rift is full of detail. Instead of a smooth, dark lane, it breaks into intricate filaments and knots, shaped by turbulent gas and magnetic fields. Within those dark clouds are stellar nurseries, places where new stars are forming by the thousands. The same dust that hides the Milky Way's light also creates the conditions for its renewal. The influence of dust on the naked eye view of the galaxy is profound. Ancient skywatchers noticed these dark gaps long before modern astronomy. The Inca, for example, saw animals in the black shapes of the rift, interpreting the voids as llamas and serpents. The Aboriginal Australians traced the outline of an emu in the sky using the same shadows. In both cases, it was the dust lanes, not the bright stars, that defined the celestial imagery. This suggests that for human eyes, the contrast between light and darkness is as meaningful as brightness itself. From a scientific perspective, dust lanes not only alter the galaxy's appearance, but also limit our knowledge. The center of the Milky Way is home to a supermassive black hole, Sagittarius A star, surrounded by dense star clusters and energetic phenomena. Yet none of it can be seen in visible light. The dust that shapes the naked eye Milky Way also blinds us to its heart. Only by switching to radio, X-ray, or infrared wavelengths can astronomers penetrate the veil and uncover the dynamic core of our galaxy. Dust also creates subtle effects across the rest of the disk. The Milky Way is made of spiral arms filled with young, bright stars, but dust tends to line the inner edges of those arms, where gas is compressed by density waves. The result is that when we look at other spiral galaxies, like Andromeda, the spiral arms are traced not only by bright starlight, but also by dark dust lanes running alongside them. Our galaxy looks much the same, though from within the pattern is harder to discern. To the unaided eye, the Milky Way's disk appears broken into patches of brightness and shadow, stitched together by dust. On a more local scale, the Coal-Sack Nebula in the southern hemisphere is one of the most striking dust features visible without a telescope. Just next to the Southern Cross, it appears as a large, inky void, utterly devoid of stars. For centuries, observers thought it was a hole in the heavens. Now we know it is a nearby dark cloud, perhaps 600 light-years away, blocking the light of the galactic bulge beyond. The coal sack is a reminder that the Milky Way's appearance depends as much on what we cannot see as on what we can. Without dust, the Milky Way would look far brighter and more uniform. The galactic bulge would shine with unbroken brilliance, the disk would be filled with stars to the limit of our vision, and the great rift would vanish. The sky would not have its current dramatic contrast between light and shadow. Ironically, the very features that make the Milky Way visually striking, the patterns of brightness and darkness that give it texture, are due to the dust that blocks our view. What appears to be a flaw in the cosmic picture is, in fact, its defining artistry. This interplay between obscuration and revelation is part of what makes the study of dust so compelling. On Earth, dust is a nuisance, something to be wiped away. In the sky, it is both obstacle and guide. It hides the center of our galaxy while pointing us toward its structure. It robs the Milky Way of brightness while giving it character. And in those same dark lanes, invisible to the naked eye, it shapes the birth of future generations of stars. To step outside on a clear night and see the great rift bisecting the Milky Way is to witness this paradox directly. It is darkness, but not emptiness. It is absence, but also presence. It is the mark of dust sculpting the face of the galaxy we call home. On a warm summer night in the northern hemisphere, when the air is still and the world is quiet, you can look up and see the Milky Way arching high overhead. From the constellation of Cygnus, with its bright star Deneb, down through Aquila, past the star Altair, and onward towards Sagittarius, the galaxy splits in two. Instead of a single glowing river, you see two streams of starlight divided by a wide, dark lane. To the naked eye, it looks like a wound cut into the heavens, a seam of darkness running the length of the sky. This is the Great Rift. For anyone seeing the Milky Way from a truly dark sight for the first time, the Great Rift is unforgettable. It is not subtle. The divide runs for more than 30 degrees across the sky, stretching like a gash from horizon to horizon. In Cygnus, the rift begins broad and obvious, with thick lanes of shadow cutting straight through the bright heart of the Milky Way. As you trace it downward toward Aquila, the gap narrows, then widens again, before dissolving into the glow around Sagittarius. To the eye, it feels like a canyon in the stars, a river of darkness separating two bright banks of light. What you are really seeing is the effect of vast molecular clouds lying between us and the more distant stars of the Milky Way's inner spiral arms. These clouds are enormous, each hundreds of light-years across, filled with dust grains that scatter and absorb visible light. The closest of these clouds are only about 300 to 600 light-years away, practically next door on galactic scales. That means the Great Rift is not some distant feature at the edge of the galaxy, but a relatively nearby veil, blotting out the background stars. When Galileo first pointed his telescope at the Milky Way in 1610, he revealed that its glow came from countless individual stars. But even his primitive optics showed that parts of the Milky Way were strangely lacking in starlight. He couldn't explain why. Later, observers catalogued these voids, often assuming they were gaps in the distribution of stars. It wasn't until the 20th century, with Robert Trumpler's work on interstellar extinction, that the truth became clear. The Great Rift was not a hole in the galaxy, but a curtain of dust clouds lying in front of it. For the casual observer, the rift is best seen in summer, when the constellations of Cygnus and Aquila are high overhead. Binoculars reveal its structure in greater detail. Instead of a single dark stripe, you notice that the rift is broken into smaller lanes and pockets, each with slightly different opacity. These correspond to individual clouds, some thicker, some thinner, stitched together into the grand feature we call the rift. Through binoculars, the edges are particularly striking, sharp contrasts between dense dark clouds and glittering star fields just beyond. It is like looking at storm clouds backlit by lightning, except here the storm is silent and centuries deep. A small telescope can add even more nuance. Within the rift, you see bright patches where starlight leaks through, clusters of young stars peeking out from behind the dust. Many famous objects lie along its path. The North America Nebula in Cygnus, for example, is just on the edge of the rift, glowing in hydrogen light while dust clouds shape its outline. The dark nebula known as the Cygnus Rift forms part of the northern stretch, a dense region of obscuration crisscrossing the constellation. The rift is not a uniform wall, but a complex, layered tapestry. Some parts are only a few hundred light-years away. Others lie farther, superimposed along the same line of sight. Astronomers in the 19th and early 20th centuries began systematically mapping these dark clouds. Edward Emerson Barnard, an American astronomer, created a famous catalogue of dark nebulae in the early 1900s. Using wide-field photographs, he identified and numbered hundreds of patches of darkness across the sky. Barnard's meticulous plates showed that the Great Rift was not a single monolithic feature, but a series of overlapping dark nebulae stretching along the galactic plane. Many of these still carry his name today: Barnard 147, Barnard 168, and so on, little fragments of the larger puzzle. By studying the stars in and around these clouds, astronomers determined their approximate distances. In the northern Cygnus Rift, many of the dark clouds are around 500 light-years away. In Aquila, some lie closer, around 300 light-years. These numbers come from comparing the brightness and color of stars seen through the dust with those of similar stars outside it. The reddening effect of dust provided the clue. The redder the starlight, the more dust lay in between. By calibrating this effect, scientists could measure not only the thickness of the clouds, but also their location in space. One of the most surprising findings is just how thin the Great Rift is compared to its length. Across the sky, it stretches for thousands of light-years in projected distance, but its nearest portions are relatively close to Earth. That means we are peering through a long corridor of dust clouds, aligned almost perfectly with our line of sight, giving the illusion of a continuous dark river. In reality, it is a chain of clouds, each shaped by turbulence, star formation, and magnetic fields, overlapping to produce the grand shadow we see. Infrared astronomy has transformed our understanding of the rift. Satellites like IRAS and Spitzer have imaged the region in wavelengths invisible to the eye. In these images, the dark lanes shine brightly, glowing with the heat of warmed dust. Structures hidden in visible light appear in astonishing clarity: filaments, knots, and vast sheets of dust stretching for hundreds of light-years. The rift, once seen only as darkness, is revealed as a luminous, active environment filled with forming stars. Within its clouds lie stellar nurseries. Protostars, still wrapped in cocoons of dust, slowly contract under gravity, heating until nuclear fusion ignites. These regions are invisible in optical light, but blaze in the infrared. Astronomers now know that the Great Rift is not simply a barrier to starlight. It is a cradle of stars, one of the most active nearby regions of star formation in the galaxy. The irony is striking. What looks like emptiness to our eyes is actually one of the most productive regions of creation. From a cultural perspective, the rift has always drawn the imagination. The Inca traced llamas and foxes in its shapes. In North America, some native peoples saw the rift as the path of departed souls. To others, it was a road to the afterlife or a scar dividing the heavens. Its prominence in the night sky ensured that it became part of mythologies across continents. What people saw as darkness, they interpreted as meaning. The rift carried symbolism precisely because it stood out so clearly against the backdrop of stars. For modern stargazers, the rift serves as both a challenge and a guide. Amateur astronomers know that within those dark clouds lie treasures, emission nebulae, star clusters, hidden galaxies peeking through gaps. The rift gives the Milky Way texture, turning it from a bland streak of light into a landscape with depth and contrast. Without it, the summer sky would be less dramatic, less alive. In the grand scheme of the galaxy, the Great Rift is just one set of dust lanes among many. But from Earth, it is our rift, the most prominent reminder of how dust shapes our view of the cosmos. It marks the boundary between what we can see and what is hidden. It is close enough to study in detail, yet vast enough to humble us with its scale. And every summer, when it rises again, it invites us to look upward and remember that even in the darkest places, there is creation at work, hidden just beyond the light. If the Milky Way's dust lanes were nothing but darkness, we might still believe them to be voids in the heavens. What makes them visible to science is not what they block, but what they reveal in other ways. Over the past century, astronomers have learned to look beyond visible light, to use the entire spectrum of radiation, radio waves, infrared, ultraviolet, even X-rays, as tools for seeing the invisible. Dust lanes, once opaque mysteries, have become some of the richest laboratories in astrophysics. The first great breakthrough came from radio astronomy in the mid-20th century. In 1951, Dutch and American scientists detected the 21-centimeter line of neutral hydrogen, a faint radio signal emitted when the spins of a hydrogen atom's proton and electron flip alignment. Unlike visible light, this signal can travel through dust unhindered. Suddenly, astronomers could map the gas distribution of the Milky Way without the interference of extinction. What they found was astonishing. The galaxy's spiral arms traced out in vast filaments of hydrogen, much of it overlapping with the dust lanes. The darkness seen in visible light was not emptiness, but the most gas-rich parts of the galactic disk. But hydrogen alone is not enough to form stars. For star formation, gas must be cold and dense, existing in the form of molecular hydrogen. Unfortunately, molecular hydrogen is nearly invisible in most wavelengths. Instead, astronomers use carbon monoxide, CO, as a tracer. CO emits strong rotational lines in the millimeter range, which radio telescopes can detect. Surveys of CO across the Milky Way revealed enormous molecular clouds stretching for hundreds of light-years, many of them aligned with the Great Rift and other dust lanes. By combining hydrogen and CO data, astronomers built a three-dimensional picture of the interstellar medium. Hydrogen outlining the broad spiral structure, CO marking the densest regions where stars are born, and dust lanes corresponding to the most obscured zones. While radio astronomy let us trace the gas behind the dust, infrared astronomy allowed us to see the dust itself. Dust grains, though cold, absorb starlight and re-radiate it as heat, glowing faintly at infrared wavelengths. In 1983, the Infrared Astronomical Satellite, IRAS, conducted the first all-sky survey in the infrared. For the first time, the Milky Way's dust lanes lit up as glowing filaments, bright and intricate. Regions that looked like darkness in visible light became luminous rivers in infrared, full of structure and detail. Later missions refined this view. The Spitzer Space Telescope, launched in 2003, captured the galactic plane in mid-infrared with unprecedented resolution, revealing dust filaments like threads of smoke twisting through star-forming regions. The Herschel Space Observatory, operating from 2009 to 2013, extended the view into far infrared and sub-millimeter wavelengths, sensitive to the coldest dust. Herschel's maps showed enormous networks of filaments, structures hundreds of light-years long, where dust and gas collect and fragment into dense cores that eventually collapse into stars. More recently, the James Webb Space Telescope has taken this further, producing images where dust is no longer a flat silhouette, but a textured, glowing medium full of knots and tendrils. What once appeared as absence is now revealed as complexity. In addition to direct imaging, astronomers use clever techniques to measure dust indirectly. One is extinction mapping, comparing the brightness of stars behind dust clouds with those outside them. If a star of known type appears fainter and redder than expected, the difference can be attributed to dust along the line of sight. By repeating this measurement across thousands of stars, astronomers can create detailed maps of extinction, showing where dust lies and how thick it is. With modern surveys like Gaia, which measures distances and intrinsic brightnesses of over 1 billion stars, extinction maps have become astonishingly detailed, giving a three-dimensional view of dust distribution across the galaxy. Another tool is polarization of starlight. When light passes through interstellar dust grains that are aligned by magnetic fields, it becomes polarized, meaning the electric field of the light waves vibrates preferentially in one direction. By measuring the polarization of starlight, astronomers can not only detect the presence of dust, but also infer the orientation of magnetic fields within the clouds. This has revealed that dust lanes are not random clumps, but are shaped and guided by galactic magnetism. Herschel, Planck, and now Webb have all contributed to this understanding, showing that filaments often align with magnetic field lines, suggesting that magnetic pressure plays a role in controlling star formation. The study of dust has also advanced through spectroscopy. Silicate grains, for example, leave a characteristic absorption feature around 10 microns in the infrared, caused by the stretching of silicon-oxygen bonds. Carbonaceous grains produce their own unique features. By analyzing the spectra of stars and nebulae filtered through dust, astronomers can deduce what the grains are made of. This technique confirms that dust is not uniform, but a mix of silicates, carbon, ice, and complex organic molecules, varying with environment. The combination of these methods has turned the Great Rift and other dust lanes from mere shadows into richly mapped structures. Instead of voids, we now see layers: cold hydrogen traced in radio, dense cores in CO emission, glowing dust in infrared, magnetic fields revealed by polarization. Each technique adds another layer of information, like peeling back the masks of the same object seen in different light. The impact of these studies reaches far beyond the Milky Way. By learning how to correct for extinction and measure dust properties, astronomers can study distant galaxies with greater accuracy. When light from a far-off galaxy passes through the Milky Way's disk, extinction must be accounted for, or else distances and brightnesses will be underestimated. Dust lanes are not just a local curiosity, they are a fundamental part of cosmic measurement itself. And there is a poetic side to this. Every tool humanity has devised to study dust lanes represents a way of extending our senses. Our eyes cannot see radio waves, yet with radio dishes we can hear hydrogen whispering across thousands of light years. We cannot see heat in the far infrared, yet with satellites like Herschel we can watch the coldest dust glow. We cannot sense polarization, yet our instruments reveal the invisible geometry of magnetic fields sculpting the clouds. The universe hides its deepest workings in wavelengths beyond human vision, and dust lanes, once symbols of obscurity, have become gateways to discovery. To stand under the night sky and see the Great Rift is to confront the limits of human perception. To place a radio dish in a desert or launch a telescope beyond Earth's atmosphere is to transcend those limits, turning shadows into maps and darkness into detail. The dust lanes of the Milky Way, once thought to be nothing at all, now tell us more about the galaxy's structure, evolution, and future than almost any other feature of the night sky. When you look at the Milky Way on a summer night, the dust lanes stand out as dark interruptions, as though someone had smeared charcoal across the stars. But hidden inside those shadows lies something far more dynamic than the stillness they suggest. They are not only obscuring light, they are creating it. Dust lanes are where stars are born. The process begins in molecular clouds, immense reservoirs of cold gas and dust. These clouds are sometimes called stellar nurseries, and the name is apt. Inside them, gravity, chemistry, and physics conspire to turn raw interstellar material into new suns. They are among the coldest objects in the universe, with temperatures often just 10 to 20 degrees above absolute zero. At such frigid conditions, atoms of hydrogen pair up into molecules, forming H2, molecular hydrogen, the dominant ingredient of these clouds. Dust plays a central role here. Without it, gas in the galaxy would not cool enough to collapse. Dust grains act like tiny radiators, absorbing heat and emitting it in infrared. This cooling effect allows clumps of gas to grow denser under gravity without being blown apart by thermal pressure. In addition, dust grains provide surfaces for chemistry. Molecules like water, carbon monoxide, methane, and even more complex organics can form on their surfaces, coating them with icy mantles. These icy grains are the raw seeds from which new worlds will eventually emerge. Inside a dust lane, the molecular clouds can be enormous. The Orion molecular cloud, one of the nearest, stretches over 240 light-years and contains thousands of times the mass of the Sun. Within it lies the Orion Nebula, a glowing pocket just visible to the naked eye as a faint smudge in Orion's sword. With binoculars or a telescope, the Orion Nebula becomes a luminous cloud, and within it, hidden in dust, new stars are forming in clusters. Some are already hot enough to ionize surrounding gas, lighting up the nebula in a soft glow. Others remain in darkness, still wrapped in cocoons of dust, invisible until infrared telescopes reveal them. Another iconic site is the Eagle Nebula in the constellation Serpens, home to the so-called Pillars of Creation. Immortalized by the Hubble Space Telescope in 1995, the image shows towering columns of dust and gas, each several light-years tall. Inside those pillars, stars are being born, their radiation slowly eroding the structures from within. What looks like static sculpture is in fact a dynamic battle, gravity pulling inward to form stars, radiation pushing outward to disperse the dust. In time, the newborn stars will carve the pillars apart, but for now, they remain one of the most vivid illustrations of dust as both a veil and a womb. The interplay of dust and starlight is paradoxical. On one hand, dust lanes obscure the galaxy, hiding the brilliance of background stars. On the other hand, they are essential for the creation of new stars. Without dust, the gas would not cool enough to fragment into the dense clumps needed for star formation. Dust both conceals and enables, the great paradox of cosmic shadow. Astronomers studying these regions rely heavily on infrared and radio observations. Visible light shows only silhouettes, but in infrared, the clouds glow, revealing embedded protostars. In radio, molecules like carbon monoxide trace the dense gas filaments. Observations of the Orion Nebula, for example, have identified disks of dust around young stars, protoplanetary disks that may, in millions of years, condense into planetary systems. We are watching not only the birth of stars, but the birth of worlds. The scale of star formation in these dust lanes is staggering. In a typical giant molecular cloud, hundreds of stars can form at once, often in clusters. Our Sun is thought to have been born in such an environment about 4.6 billion years ago, alongside many siblings that have long since drifted away. The dust lanes we see today are the same kinds of environments that gave rise to our planetary system. To look at them is, in a way, to look back at our own origins. The life cycle of these clouds is also shaped by feedback from the stars they create. Massive stars form quickly, burn hot, and pour out intense ultraviolet radiation. That radiation ionizes the gas around them, carving glowing bubbles and pushing back the dust. Eventually, supernovae from those massive stars will blast the clouds apart, dispersing dust and enriching the interstellar medium with heavy elements. Thus, dust lanes are temporary structures, lasting tens of millions of years, a blink of an eye in galactic time. They are constantly forming, fragmenting, and dissipating, part of the galaxy's endless recycling. Some of the most famous dust-filled nurseries are visible even to amateur observers. The Lagoon Nebula in Sagittarius, the Trifid Nebula with its dark dust lanes splitting it into three, the Horsehead Nebula in Orion, and the Carina Nebula in the southern hemisphere. Each is a masterpiece sculpted by dust and starlight. They show the dual nature of dust, sculptor and destroyer, obscurer and enabler. Theories of star formation continue to evolve, but dust is always at the center of them. It is not merely passive, but active. It dictates cooling rates, chemistry, and even the initial mass distribution of stars. Without dust, the Milky Way would not look the way it does, nor would it continue to create new generations of stars and planets. It's humbling to think that the darkness we see in the night sky is not emptiness, but fertility. The Great Rift, the Coal Sack, the Pipe Nebula, all those silhouettes that carve the Milky Way's glow, are places where the future of the galaxy is being written. Somewhere inside them, right now, stars are igniting that will shine for billions of years, perhaps with planets that will host life. And all of it begins in the cool embrace of dust. When we look at the Milky Way from within, the dust lanes appear as local interruptions, streaks of shadow cutting across the stars above us. But if we could step outside our galaxy, if we could see it from millions of light years away as we see Andromeda or the Sombrero Galaxy, the pattern would be unmistakable. Dust is not scattered randomly. It is organized, sculpted into sweeping lanes that trace the very skeleton of galactic structure. The Milky Way is a barred spiral galaxy, a disk of about 100,000 light-years in diameter, with graceful arms that curve outward from a central bar. These spiral arms are not material objects in themselves, but density waves, like traffic jams that move through the disk, compressing gas and dust as they pass. Where the compression is strongest, gas clouds collapse, stars form, and dust lanes appear. The arms are lit with young hot stars, and alongside them lie the shadows, long streaks of interstellar dust that outline the spirals. In photographs of distant spiral galaxies, this relationship is easy to see. Look at Andromeda, our nearest large galactic neighbor, 2.5 million light-years away. Its bright disk is crossed with dark bands, looping like rivers of shadow along the spiral arms. The dust lanes appear darker than the surrounding disk, not because they contain more matter than the stars, but because they block our line of sight. Against the glow of billions of stars, the dust clouds stand out in stark relief. Our own galaxy must look similar from afar. Along the Scutum Centaurus arm, the Perseus arm, and others, dust lanes would stretch like ink strokes, parallel to the arms of starlight. They would not be smooth. Infrared and radio maps show that dust in the Milky Way is clumpy and filamentary, broken into irregular patches. But from the outside, the grand pattern would dominate, spirals of light threaded with spirals of shadow. Barred spiral galaxies, like the Milky Way, show another striking feature: dust lanes that run along the central bar itself. In high-resolution images of galaxies such as NGC 1300 or NGC 1097, the bar is flanked by twin streaks of darkness, feeding gas inward toward the core. These bar dust lanes act like galactic highways, channeling matter from the arms into the center, where it can fuel bursts of star formation, or even feed a central black hole. The Milky Way shows the same signature. Radio observations of gas and infrared imaging of dust reveal two enormous lanes funneling material along the bar toward the galactic nucleus. They are not subtle features. They are colossal structures, each thousands of light-years long, shaping the flow of matter across the galaxy. Dust distribution is not uniform, even within the arms. Spiral arms often show a kind of sequence. At the leading edge, gas and dust are compressed by the density wave, forming dust lanes. Just behind, stars begin to form, and farther still, massive young stars blaze, lighting the arms with ultraviolet radiation. The dust, in a sense, leads the way, marking the places where new stellar generations are just beginning to emerge. Comparing galaxies makes the role of dust even clearer. Andromeda, with its wide disk and relatively moderate star formation, shows dust lanes that are distinct but not overly thick. The Sombrero Galaxy, by contrast, presents a spectacular view, a bright, round bulge wrapped by a razor-thin dust lane. At a distance of about 30 million light-years, the Sombrero appears like a broad-brimmed hat. Its bulge glows with the light of old stars, while a dense dark band of dust encircles it like the brim. Here, dust is not an accent. It is the defining feature, slicing the galaxy's profile into light above and shadow below. Other galaxies show dust in more chaotic arrangements. In irregular galaxies, or those stirred by collisions, dust lanes can warp, twist, or scatter. The Whirlpool Galaxy, M51, famous for its grand design spirals, has dust lanes that curl tightly around its luminous arms, showing where the interstellar medium is densest. In interacting galaxies, dust can be torn into bridges and tails, stretched across tens of thousands of light-years. The Milky Way, though we cannot see it from outside, is part of this continuum. Observations from surveys like COBE, IRAS, and Gaia have mapped its dust with increasing precision. What emerges is a picture of lanes and filaments aligned with the spiral arms, with thicker concentrations near the bar and bulge. From our vantage point, the dust obscures our view of the center, but in infrared, the lanes glow with energy, tracing the flow of material across the galaxy. Dust is not confined to the disk alone. Some grains are lifted into the galactic halo by supernova explosions, carried on winds of hot gas. There, far above the plane, they scatter ultraviolet light from young stars, producing faint glows detected by sensitive instruments. Even in the galactic outskirts, dust is present, though thin and diffuse. It is, in a sense, everywhere, an essential component of the galactic ecosystem. What makes dust lanes so visually striking in galaxies like Andromeda and the Sombrero is the contrast. Against the overwhelming brightness of starlight, even a modest amount of dust creates sharp silhouettes. The same principle explains why we see the Great Rift so clearly from Earth. The dust is not especially dense by human standards. If you scooped up the material filling a cubic centimeter of interstellar space, you would find only a few hundred atoms, far less than the best laboratory vacuum. But stretched across light years, that thin haze is enough to block the view of distant stars, just as a wisp of smoke can hide the flame of a candle when viewed from afar. From a scientific perspective, the distribution of dust provides a roadmap to galactic evolution. Dust marks where gas is dense, where new stars will form, and where feedback from existing stars is reshaping the medium. By mapping dust lanes, astronomers can trace the skeleton of spiral arms, measure the flow of material into the core, and compare the life cycles of galaxies across the universe. From a human perspective, there is something haunting about these comparisons. To look at Andromeda and see its dark lanes is to glimpse, in a sense, a reflection of our own home. Somewhere, if an observer were watching the Milky Way from 2 million light-years away, they would see our galaxy with the same dark streaks, the same luminous arms, the same obscuring shadows. They would see the dust lanes of the Great Rift cutting across the galactic plane just as we see them in Andromeda. The patterns that seem so particular to our night sky are, in fact, universal, written into the architecture of spiral galaxies everywhere. And perhaps this is what makes dust so compelling. It is not confined to a single place or culture. It is part of the grand design of galaxies. The shadows that cut across our Milky Way are the same kinds of shadows etched into Andromeda, the Sombrero, and countless others scattered across the cosmos. Dust, so tiny on the scale of grains, becomes monumental on the scale of galaxies, shaping the face of the universe itself. The dust lanes of the Milky Way might seem like static features, frozen shadows on the sky. But in truth, they are part of an ongoing process, woven into the life cycle of the galaxy itself. Dust is not only a byproduct of stellar death and a prerequisite for stellar birth. It is also one of the main agents driving the evolution of galaxies. Every generation of stars alters the dust content of the interstellar medium, and that dust in turn influences how the next generation of stars and planets will form. The cycle begins with stars themselves. Throughout their lifetimes, stars shed material in stellar winds, streams of gas that flow outward into space. Our Sun loses about 1 million tons of matter every second in its solar wind, though compared to its total mass, that is a faint whisper. More massive stars, however, lose mass at a staggering rate. Hot, luminous O-type stars can drive powerful winds that sweep entire regions of space, compressing and sculpting nearby gas and dust. These winds are not just gentle breezes. They are supersonic, tearing into the surrounding medium and altering its structure. Then comes the more dramatic feedback, supernovae. When a massive star reaches the end of its life, it explodes, releasing energy on a scale almost unimaginable. A single supernova can outshine an entire galaxy for weeks. The blast wave races outward at thousands of kilometers per second, slamming into the surrounding interstellar medium. In its wake, shock waves compress clouds, trigger new rounds of star formation, and at the same time, destroy existing dust grains. Yet, paradoxically, supernovae also create dust. As the ejected material expands and cools, heavy elements condense into fresh grains, silicates, carbon compounds, metallic oxides. Observations of supernova remnants like Cassiopeia A show vast amounts of dust glowing in infrared, newly minted from the ashes of a dead star. This balance, destruction and creation, erosion and renewal, is central to galactic evolution. Dust is constantly being ground down by shocks, sputtered away by high-energy radiation, and reassembled in stellar outflows. Over billions of years, this recycling enriches the interstellar medium with heavy elements, what astronomers call metals, everything heavier than hydrogen and helium. The universe began nearly devoid of such materials. After the Big Bang, the cosmos was almost pure hydrogen and helium, with only trace amounts of lithium. The first stars, the so-called population 3 stars, had no metals at all. When they exploded, they seeded the universe with the first carbon, oxygen, silicon, and iron. Dust could not form until those elements existed. In a sense, dust is the signature of a maturing universe, evidence that generations of stars have lived and died. In our galaxy today, dust accounts for about 1% of the mass of the interstellar medium. That might seem trivial, but its influence is outsized. Dust regulates the temperature of clouds by absorbing ultraviolet and visible light and re-radiating it in the infrared. It shields fragile molecules from destructive radiation, allowing complex chemistry to take place in the shadows. And it seeds the formation of planets, as tiny grains stick together in protoplanetary disks and grow into pebbles, planetesimals, and eventually worlds. The chemical evolution of galaxies cannot be understood without dust. Each cycle of star birth and death increases the abundance of metals in the interstellar medium. With every generation, the dust grains become more diverse, enriched with new elements. This enrichment changes how gas cools, how stars form, and even what types of planets can emerge. Earth itself, with its iron core, silicate mantle, carbon-based life, is a product of billions of years of dust recycling. Without supernovae scattering elements, without dust carrying them across the galaxy, there would be no rocky planets, no oceans, no biospheres. Dust also carries the fingerprints of its origins. Silicate grains formed in oxygen-rich environments differ from carbonaceous grains formed around carbon-rich stars. Some interstellar grains collected in meteorites on Earth show isotopic ratios that mark them as pre-solar grains, older than the Sun, forged in ancient stars that died before our solar system was born. These tiny inclusions, studied under microscopes in terrestrial labs, are literal time travelers, fragments of stars from before the solar system, preserved in dust and delivered to Earth. They tell us that the dust lanes we see today are part of a story that stretches back long before our planet existed. Dust's role in galactic evolution is not limited to its physical and chemical effects. It also changes how galaxies look, how we observe them, and even how we interpret cosmic history. In galaxies undergoing starbursts, rapid periods of intense star formation, dust absorbs so much starlight that the galaxies glow more brightly in infrared than in visible light. These so-called luminous infrared galaxies are powered by dust as much as by stars. In the early universe, many young galaxies were hidden by thick veils of dust, detectable only when instruments sensitive to sub-millimeter wavelengths, like the Atacama Large Millimeter/Submillimeter Array, ALMA, unveiled them. Without accounting for dust, we would have underestimated the rate of star formation in the cosmos. The interplay of dust and feedback also shapes galactic structure. In spiral galaxies, dust lanes outline the arms, but feedback from massive stars continually stirs and reshapes them. In elliptical galaxies, which lack active star formation, dust is far less prominent, often existing only in wisps left over from mergers. In dwarf galaxies, with their shallower gravity wells, supernova feedback can blow dust out entirely, enriching the intergalactic medium instead. Thus, the presence or absence of dust tells the tale of a galaxy's history and its current state of star formation. The Milky Way itself is still evolving under this cycle. Every supernova enriches the medium. Every stellar wind adds grains. Every new star carves bubbles in the dust. Over billions of years, the galaxy has transformed from a primordial metal-poor system into a dust-rich spiral, capable of supporting planets and life. And the process continues. Stars being born in Orion or Carina today are building the materials that may, billions of years from now, form new planetary systems with their own stories. It's easy to forget, when looking at the dust lanes overhead, that they are not static curtains, but dynamic participants in galactic history. Each dark patch is the residue of stars that once lived, the cradle of stars yet to come, and the transport system for elements across cosmic time. Dust is not an accident of the Milky Way. It is one of its engines, shaping its chemistry, its appearance, and its destiny. There is something humbling in this perspective. The iron in our blood, the oxygen we breathe, the silicon in our bones, all were forged in stars, scattered as dust, and reassembled into us. The galactic cycle of dust is not abstract. It is literally embodied in our existence. To look at the dust lanes of the Milky Way is to see our own history written across the sky, a reminder that we are temporary arrangements of ancient grains, carried through billions of years of stellar evolution. And just as dust enriches galaxies, it enriches imagination. For the ancients, the shadows in the Milky Way were emus, llamas, spilled milk. For astronomers, they became clues to extinction, chemistry, and feedback. For us, they are both science and story, physics and poetry. The galaxy evolves through dust, and in that dust, we find both the origins of matter and the meaning we ascribe to it. In the past, astronomers could only guess at the true nature of the Milky Way's dust lanes. They mapped shadows, noted dark patches, and speculated about empty voids. Today, however, we are living in an era where space observatories and advanced surveys are giving us tools to peel back the veil. Dust, once a mystery that obscured the galaxy, has become an object of study in its own right. And some of the most remarkable discoveries about our cosmic home have come not from starlight, but from the dust that dims it. One of the most important breakthroughs came from the Planck satellite, launched in 2009 by the European Space Agency. Planck's main mission was to map the cosmic microwave background, the faint afterglow of the Big Bang. But to see that primordial light clearly, Planck also had to account for the foreground, the emission from dust within our own galaxy. In doing so, it created the most detailed all-sky maps of galactic dust ever made. Planck measured not only the intensity of dust emission, but also its polarization. Dust grains, elongated and aligned by magnetic fields, emit light that is polarized in specific directions. By measuring this polarization across the sky, Planck revealed the structure of the Milky Way's magnetic field on vast scales. The filaments of dust that trace the galactic plane are not random. They are shaped by magnetic forces threading the disk. The resulting maps are works of art as well as science, swirls and streams of polarized light, showing the invisible skeleton of magnetism that influences star formation, gas flows, and even the dynamics of entire spiral arms. Where Planck gave us an all-sky portrait, the Gaia mission has been offering a three-dimensional perspective. Launched in 2013, Gaia is mapping over 1 billion stars with extraordinary precision, measuring their positions, motions, and brightness. By comparing the expected intrinsic brightness of stars to what we actually observe, astronomers can infer how much light has been dimmed by dust. The result is a 3D map of extinction, a reconstruction of where dust lies between us and the stars. This approach has allowed astronomers to build detailed models of nearby dust clouds. For example, Gaia has revealed that many of the dust structures around the solar system are part of a giant cavity called the local bubble, a region about 1,000 light-years across that was carved out by ancient supernovae. Our Sun happens to sit near the middle of this bubble, surrounded by a shell of dense gas and dust. By mapping extinction in 3 dimensions, Gaia has transformed dust from flat shadows into fully realized structures, giving us a sense of depth that was impossible before. If Planck and Gaia showed us the big picture, the James Webb Space Telescope, JWST, is giving us the details. Launched in December 2021, JWST is the most powerful infrared observatory ever built. Its sensitivity allows it to peer through dust clouds that would completely block visible light, unveiling the hidden heart of star-forming regions. In its first images, JWST revealed dazzling new views of the Carina Nebula, where towering cliffs of dust glow in infrared, lit from within by newborn stars. What looked like a solid wall in visible light became, under Webb's gaze, a porous and complex structure, full of cavities, filaments, and protostars just beginning to ignite. JWST has also provided insights into the chemistry of dust. Its spectrographs can identify the fingerprints of molecules frozen onto dust grains: water, carbon dioxide, ammonia, methane, ices that coat the grains in molecular clouds. These ices are the raw ingredients of planets and, potentially, life. In one of its early studies, JWST detected the most complex ices ever observed in space, suggesting that dust grains are chemical laboratories where prebiotic molecules can form. What was once dismissed as mere obscuring dirt is now seen as a stage where the drama of chemistry plays out on cosmic scales. Together, these missions give us a layered understanding of dust lanes. Planck shows us their relationship to magnetic fields. Gaia places them in 3 dimensions. JWST reveals their internal architecture and chemistry. Each mission adds a new sense: polarization, parallax, infrared vision. It is as though humanity has been blind to the true shape of its galaxy for centuries, and now, slowly, our sight is expanding across wavelengths we cannot perceive with our eyes. These discoveries also underscore how central dust is to almost every question in modern astrophysics. The study of galaxy formation, the search for exoplanets, the measurement of cosmic expansion, all depend on understanding and correcting for dust. Without Planck's dust maps, our view of the cosmic microwave background would be blurred. Without Gaia's extinction corrections, stellar distances would be distorted. Without JWST's infrared eye, the earliest stages of star and planet formation would remain hidden. And there is still much more to come. Future missions, such as the planned Nancy Grace Roman Space Telescope, will map the sky in wide-field infrared, complementing JWST's deep focus with panoramic views. Ground-based observatories like ALMA in Chile continue to probe the sub-millimeter emission of dust, resolving filaments and disks at exquisite resolution. Together, they will refine our knowledge of how dust lanes evolve, how they connect with magnetic fields, and how they set the conditions for star birth. What is striking, perhaps, is the way dust has shifted in perception. For centuries, it was seen as a nuisance, a veil blocking the stars. Even in modern astronomy, dust was at first considered a contaminant, something to be subtracted, corrected for, in order to see the real universe behind it. But now, dust has emerged as a subject in its own right, no longer an obstacle, but a messenger. By studying it, we learn not only about the stars it conceals, but about the processes of creation that occur within it. To walk outside and see the great rift dividing the Milky Way is to see the very same dust that Planck has mapped, that Gaia has charted in 3D, that JWST has revealed in infrared glory. The dark river above is not absence, but abundance, a feature of the galaxy that modern missions have turned from mystery into knowledge. And as we continue to refine our instruments, we are reminded that even the darkest parts of the sky are filled with light, just not in wavelengths we can see. There is a phrase that has echoed through cultures and centuries: dust to dust. It is usually spoken in the context of endings, a reminder of mortality, of the body's return to the earth. But in the context of the galaxy, the words take on a different resonance. Dust in the Milky Way is not only a symbol of decay, it is also a symbol of renewal. It is the link that ties together death and creation, stars and planets, life and the universe itself. Every dust lane that cuts across the night sky is a reminder of this connection. Those dark streaks are filled with grains forged in the cores of ancient stars. Some came from quiet red giants shedding their outer layers, others from supernovae, violent and luminous, scattering their ashes across space. Each grain carries with it the memory of its origin. Silicon atoms fused in the belly of a giant star, carbon atoms built in its final breaths, iron and nickel forged in the blast of collapse. What looks like a shadow in the sky is actually the combined history of billions of stars that once lived and died. And those grains are not inert. They drift, collide, and merge. They become coated with ices, participate in chemistry, and act as scaffolding for molecules. They cool gas so that new stars can form. Around those newborn stars, the grains settle into disks, clump into larger aggregates, and eventually form planets. The dust lane we see above us tonight could, in 100 million years, be the birthplace of a new solar system, a star with rocky worlds, oceans, atmospheres, maybe even living beings wondering about their own origins. There is a paradox at the heart of dust. It hides the light of stars, yet it is the very reason those stars can exist. To our eyes, the Great Rift looks like absence, but inside it is creation. Dust blocks our vision while enabling the processes that ensure the galaxy's continued vitality. It is both veil and womb, concealer and nurturer. Without it, the Milky Way would blaze more brightly, but it would also be sterile, deprived of the material needed to build worlds. In that sense, darkness is not the enemy of light. It is its partner. For humans, this paradox is not only scientific, but also symbolic. We are, in a literal sense, the children of dust. The calcium in our bones, the carbon in our cells, the oxygen we breathe, the iron coursing in our blood, all of it was once part of interstellar dust. Before the Earth formed, before the sun ignited, those atoms floated in the dark clouds of the Milky Way, invisible and unremarkable. They gathered, clumped, collapsed, and became us. To say we are stardust is not poetic license. It is the most literal truth science has to offer. This makes the dust lanes of the Milky Way strangely intimate. They may seem remote, thousands of light years away, but they are also the origin of everything we know. To stand beneath the summer sky and see the Great Rift is to see, in silhouette, the source of ourselves. That shadow is not an absence to be feared, but a presence to be revered. It is our ancestor, our birthplace, our inheritance. And there is comfort in the cycle. Just as stars die and leave behind dust, so too will our sun, 5 billion years from now, shed its outer layers into space. Earth and its inhabitants will be gone, but the material will remain. The atoms that are now part of us will one day drift in the interstellar medium, perhaps to be incorporated into a future star or planet. We too will return to dust, not as an end, but as a continuation of the galactic story. Seen this way, dust lanes are less like scars across the Milky Way and more like veins carrying the lifeblood of the galaxy from one generation to the next. They connect past and future, death and birth. They remind us that the universe is not a static thing, but a process, constantly recycling itself, constantly turning shadows into light, and light back into shadows. Even the aesthetic experience of dust carries meaning. The contrast between the glowing band of stars and the dark rift is what makes the Milky Way visually striking. If the sky were uniform without dust, it would be flatter, less textured. It is the interplay of brightness and obscuration that gives the galaxy its character. This duality mirrors existence itself. Joy shaped by sorrow, life shaped by death, creation shaped by destruction. Dust lanes embody this duality in cosmic form. The ancients sensed some of this, even without knowing the science. To the Inca, the dark shapes were llamas, foxes, serpents, living beings hidden in the sky. To the Aboriginal Australians, The dust lanes formed the emu in the sky, a figure woven into the rhythms of hunting and gathering. They saw not absence, but presence, not emptiness, but life. Modern astronomy, with all its telescopes and instruments, has arrived at the same conclusion by another path. The darkness is full. The shadows are alive. And so, at the end of this journey through the dust lanes of the Milky Way, we arrive not at emptiness, but at wonder. What once seemed like flaws in the starry sky turn out to be the most vital parts of it. What once obscured our view turns out to be the very material that made us possible. To step outside and look up at the dark rift cutting through the Milky Way is to stand at the intersection of science and poetry. It is to know, on the one hand, that you are looking at silicate grains coated in ice scattered across hundreds of light years. And on the other hand, it is to feel, deep in your being, that those grains are your kin, your history, and your future. It is to understand that dust to dust is not a sentence of finality, but a promise of renewal. The dust lanes are the galaxy's memory. They record every star that has lived, and they contain every star that will come. They are both veil and revelation, hiding the light while hinting at a deeper story. And they invite us always to look again, not at what is missing, but at what is waiting within the shadows. And that brings us to the end of this journey. The dust lanes of the Milky Way, shadows across the stars, turn out to be so much more than darkness. They are history, memory, and creation, woven into the galaxy itself. As you drift off, remember that the same dust-hiding light in the sky also built the earth beneath you and the life within you. From dust we come, and to dust we return. And in that cycle, the universe keeps writing its story. Thank you for listening and for sharing this quiet time. Rest well, and let the stars, and the dust between them, keep you company tonight.